Hello, it's time to start talking about, or talk a little bit about in this course about application performance. And in particular, of course, since we're building web applications, we should talk about web application performance. So we're going to hit upon some things today. We're going to talk about some basic things that we should, some vocabulary we should know and understand about performance. Then we're going to look at some basics about how to improve or be aware of some things that trip us up with web app performance. What's the basic setup that we're dealing with though? So again, let's remind ourselves. So we have, or we hope to have, of course, lots of users. You know, user 1, user 2, and up to some user n, and they're all happily out there and they're using our website. And so we've got a nice server for ourselves. This is a server with our Rails app on it. So I've got this machine. It has sitting on it the actual web server, which talks to the Rails app, which is sort of this business logic, whatever. It's an in-between application. And our Rails app, we make use of a database because we want to have a persistent setup. We want data, we want it to save and all that sort of, you know, all this stuff by now. Anyway, so we've got users and they're connecting with their web browsers, making requests. Requests come in, responses come out. The server, it has many different connections to the database. You know, it's not necessarily one for the users or whatever, but we've got connections. So we've got a machine, and each user is most likely on their own personal machine as well. And how is this system going to respond, and how should we characterize it and understand its responsiveness, its speed, its performance, and so forth and so on? One of the things, for example, you know, I could spend an entire course talking about information systems performance, the way to model it, all the things we need to understand about it. I'm not going to be able to do that today, okay? We're not going to be able to really get into the details of multiple cores on CPUs and all sorts of other stuff. So there's a lot of computer science concepts that we would need to cover first. We don't have time for that. But some things to know. I mean, one thing to keep in mind is, you know, how can this all work in an efficient manner such that these users don't realize or are impacted by the other users with regard to performance. So one of the things, you know, that we have, just to give you some sense of this, our server, our web server has multiple processes running, actually. And each process has multiple threads. And already, I am struck with, wow, how am I going to explain all this? Well, the thing to keep in mind, part of the thing is, so requests come in, and they come into Puma, the web server, and it actually has the capability to know that it may have what we call forked itself, made copies of itself into multiple running processes. So a single running process is just a program that's running. But we can have copies of them. All right, that's cool, because especially when we have multiple cores and multiple CPUs, all these sorts of things, that tends to allow us to then have multiple programs running. Okay, and you're like, well, we always have multiple programs running. Multiple programs running at exactly the same time. A CPU has certain amounts of parallelism and all sorts of stuff, but if we want lots of parallelism, we need multiple cores and multiple CPUs. Anyways, so we can have multiple processes. And a request for user 1 could be handled by one of those processes, and the request from user 2 could be handled by a different one of those processes simultaneously. And that's great. You know, this system is able to handle lots of requests at the same time. And likewise, we could have multiple requests come into the same process, but it could actually then be handled by multiple threads within that process and still, again, being able to have this concurrency, this parallelism going on. Likewise, our database sits on a server and it's got actually probably, you know, if we're really beefy, it's got lots of CPUs and cores and all sorts of good stuff. And it also is designed to have been written to have sort of a maximal ability to be concurrent and all my words aren't coming out today, to be able to do all the stuff that we need it to do. You know, there's a ton of work to increase the ability of these systems to handle concurrent requests. What do we need to know though? Okay, the big thing is to keep in mind is this big but. All right, so there's, yeah, we're gonna have all this multiple stuff and it's gonna be able to run concurrently, but any shared resource has the potential other requests. So any shared resource blocks other requests that need it. Now that's in a simple sense. It's not always the case with regard to like if we can read data, often multiple requests can read the same set of data and they won't block. But if anyone is changing and modifying some data, we need to put a lock on it so that only one person can modify it at a time. In general, anything that's shared is a source of contention. You can think again, it's like workers on an assembly line. If they both need a screwdriver, but there's only one screwdriver, so long as they don't need it at the same time, that's not a problem. But if they both need the screwdriver to do a job at exactly the same time, one of them is going to block and have to wait on the other person for that shared resource. And the same thing is very true in the computer setup as well. So we are always very we care a lot about anything that's shared in what we do, because that's where the contention, and that's where we won't be able to actually maintain this notion of parallelism or concurrent processing. So everything today that we're going to talk about really sort of comes back to dealing when the performance has a lot to do with shared resources. That's one of the big recurring themes that we're going to have. Now, if we're going to talk about performance, though, we should be talking about ways that we need to understand and measure performance. And so there's two big concepts with regard to performance and measuring it. First one is latency. And latency is the time that it takes us to respond to a user's request. So a user, does a post and, submits something to our web application. So that's the start of the request. We process it, we do something with the database, and eventually we return a response to it. The total amount of time it takes us from the time the user starts to the time it comes back to them, that's the latency. The other big thing that we need to think about, though, when it comes to performance is throughput. And throughput is the number of requests processed per unit time. Okay, so let's talk about this in more detail. Let's work with an example. Because these things are related to each other, and it takes some people some time to think about them. And I'll tell you, absolutely, having a basic grasp of latency and throughput gets you really far with being able to talk about performance and understand what's going on with systems. All right, so let's take an example system where our system can only process one request at a time. So this thing has no parallelism at all, no concurrency. All the requests basically queue up. Just a moment, please. All right, sorry for that interruption. All right, so the system can only process one request at a time. Let's say that the time to process a single request is 1 second. We have a very slow web server, but 1 second is a very convenient amount of time to have an example on. Let's say there are 10 simultaneous requests that come in. So we need to process 10 simultaneous requests. So we've got like 10 users, and they all at the same time say, give me this from the server. So we get 10 requests, they all come in. And we have a mechanism that our server can queue up the requests, but it can only actually process one at a time. So we get a request in, all right, and this thing from start to finish takes 1 second, where let's say our time is represented this way. And then to make it easy to see, we'll just draw out the next request on another line. It takes a second. And the next one takes another second. Another one takes another second, on so forth on down to our last request. Okay, so this is request 1, 2, 3, 4, all the way down to request 10. The total amount of time here from the start when things happen to the end is 10 seconds. You know, it takes 1 second for each of them. We do them with no delay, but we can only process one at a time. All right. So let's talk about things in terms of latency and throughput. So our average latency, again, latency is the amount of time it takes us to process a request. This is from the user's perspective, so it's not 1 second. This poor user down here, they put in the request, and it took a total of 10 seconds before they got their answer. This user's quite happy. They got processed and it's only 1 second. So average latency is going to be equal to, 1 plus 2 all the way up to 10 divided by, we had 10 requests. Okay, and so these are all 10 seconds, or 1, 2, up to 10 seconds. And that's equal to 55 seconds divided by 10, which is equal to 5.5 seconds per request on average. Okay, so our latency is 5.5 seconds, our average latency. Some users, their actual experience is 10 seconds and some is 1, but on average it's 5.5. So if we had a continual sort of load on the system equivalent of always about 10 items, now let's think about that. That's from the first one to the 10th one, and they all just happened at once. What actually, though, happens if we always have in a queue 10 items, 10 requests sitting around? Like we're slowly working through them, but they just keep coming in at a standard rate. Well, if they keep coming in at that rate, and we've got a queue that's 10 deep, all of a sudden our average latency is going to go to 10 seconds. But anyway, let's just say that for this example, this is what had happened, and we got 5.5 seconds per query. It's not 1 second, not query per request, all right? What's our throughput? Our throughput is equal to the number of requests we're able to do per time. So our throughput is equal to 10 requests all over 10 seconds, which happens to be, we get to do 1 request. Our throughput is 1 request per second. So we're able to process at a rate of 1 request per second, which from the definition of what we had here is completely sensible. All right. So what does a user care about? The user cares about latency. And we can see in this setup, if we can't process requests simultaneously, and in other words, we can't process simultaneous requests at the same time. Anytime more than one user is using our system, we're going to have slowdowns. The throughput is always going to, we're going to process things, it doesn't sound too bad, but we would like to be able to, for our users, we'd actually love our throughput to be able to increase. Chances are then we would be able to, their latency that they experience would be less. So let's take a little bit of a look at that now. So let's change the example. And basically, so if a system has perfect parallelism, which none ever do, but let's just pretend they do. So it can run everything. So it can process all requests at the same time. And we do the same scenario where we get 10 requests in. So now we get a request and a request and a request. They all come in at the same time, and they all get processed in the same 1 second. That's great. So now our latency is equal to 1 second. And our throughput has gone up through the roof, so to speak, and is 10 requests per second. Okay, but we always need to understand notions of throughput and latency, because sometimes we can have scenarios in systems where if you were to only be measuring throughput, okay, sometimes we have systems with good throughput and bad latency. So what does that look like? Well, that's when we've got these requests that come in, and they all are able to be processed at the same time. So we're all processing at the same time, but they take a really long time to process. So from a notion of, yep, we're churning through them, and we know the system is actually able to process them all, but for whatever reason, our actual, our latency on them is a really long time. This is when we run into this scenario, usually whether we're getting simultaneous requests or not, often our users are going to be experiencing bad latency. Anyways, so these things tend to be related. One of the things to know, though, is that depending upon the load of our system, so how many users are using it and making requests and what type of requests they are making, the latency and throughput can change as our shared resources become bottlenecks. So sort of at low load, we're probably not going to get very much contention, and we're probably not going to notice very many problems. The nature of this is, you know, our app works well up to some limit. And then the whole thing dramatically slows down. And one of the problems that we'll often see then is you got all these users, they're using your system, it's getting slower, and they're like, why isn't it returning to me? And what they'll do is they'll start, you know, hitting refresh, start doing things multiple times. They'll actually up the number of requests that you're getting all having to process at the same time. It's just a kind of a disaster. And the whole system just grinds to a halt while it's trying to churn through all these requests. Not something that we want to experience. All right, so what's our solution? You know, we have some understanding of latency and throughput now. We would always want to measure both when we're measuring a system, okay? Latency is going to let us know how the users are feeling. Throughput lets us have a sense of how much work we're able to get processed over a unit time. So what do we want? So we want to do the following when it comes to web app performance. One, we want to minimize latency to keep users happy, because if it's fast, they like it, and reduce contention. In other words, if we're able to get a request processed faster, our time that we might hold on to shared resources is by default going to be less. If we, for whatever reason, take a long time, we're likely to be tying up those shared resources longer, which then leads to more problems and so forth and so on. So latency is always something to be very concerned about. How quickly can we respond to the users? And because most of our problems are going to originate with shared resources, we want to eliminate shared resources as much as possible. So when we program, we need to be aware of whenever we're going to have resource contention, and to be thinking about that and trying to find ways that we actually won't have resource contention. So what do we need to think about to take care of the first one? Reducing latency. And this is sort of the most applicable thing to us with our basic web apps. So we can apply that, we can deal with reducing latency no matter what scale we're working at. Everyone wants our web apps to be fast and respond quickly. So this is good for everything that we're going to work on. The biggest thing that we face really is to be sure we use our database well, in an efficient manner. So what do we need to do for that? The really big thing that we need is keys used to select rows in the database table. Okay, so these are the keys. So let's say we've got a users table, and we want to select a user based upon their email address. Okay, so it's wherever we're basically whatever our where clauses are. These keys need to have indexes. Now, you might say they need to have indices, but I don't like that. I like to say indexes. Now, what's an index? Well, we talked about this in MSci 245, but as a quick refresher, an index is basically, you can think of it as, it's like a binary search tree. Okay, they're actually not usually binary trees. They're usually B trees, which is a different type of search tree. But you can think of it like a binary search tree. So we've got these big tables. They're filled with rows and rows of data. You know, we've got a gigantic like users table, you know, because we were such a popular website, and when it's now time to go fetch something about that user, we've got that user's email and we want to look it up. Well, if we don't have an index, we have to go through every single row and say, do we have a match? 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 But if we have a binary search tree, again, you know, log n time, where n is the number of rows in the table, we're able to find the record, the row for that user, and return, and you know, the other information we want, like the user's name and other sorts of stuff. So again, without an index, we do a full table scan. And a full table scan is not bad if we've got 5 users, like you're playing around with our, you know, your app as you're developing it, but it goes live and you've got a large number of users and those tables start to get big, it's a real problem. All right, so we definitely, the biggest things you need to do is make sure that you have an index placed on the important columns in your tables. So far, we've only really used indexes on columns where we wanted to, for example, enforce uniqueness. That was one of the reasons we used them. Turns out that often those columns are also the ones we're often going to query on, so it's a win-win. But there will be other columns where we want to, where we know that we're going to frequently be using them in where clauses for our queries. And again, if there's not an index on that column, we're going to have to go through and scan the entire database. Yes, there's some overhead for maintaining an index. It takes up space, takes some time to update it as we change our database. But as our tables get large, it becomes a gigantic win in performance and speed. So if you're ever working on a system and as it's growing and the data is becoming big or the query is slow, the first thing always to come to mind is, do I have the right indexes on the table for the queries that I'm running against it? So if I got a slow query, go find out what's wrong with your indexing strategy. And you can always alter a table and add an index, you know, and then, wow, we've improved the performance of our web app. We want everyone to be happy. The other thing is Rails has us use, we don't have to, but we find it convenient to use active record, which is an object relational mapping. So instead of us writing a whole bunch of SQL queries against our relational database, we're actually using, you know, these models, and and we use the various things to select the data from it. So we don't have to write lots of SQL, and that's convenient, and it also makes saving and updating. We get to work with objects rather than just a whole bunch of SQL statements. So usually it's a productivity win from a programmer standpoint, and that's really important. But we can have some efficiency issues. And so the second thing that when we deal with these web apps, and we're using one of these ORMs, object relational mapping, or manager, I guess, but ORM, we need to be mindful of has many in Rails or anywhere else where we have an ORM. Okay, so this is Rails. Actually, I should say active record, just to be clear. It's not Rails, it's the active record in Rails, which is our ORM. And so we make these associations because it's really convenient for us to be able to say, yeah, I've got this object, and I know this object has many of these other things in this other table, and so I'd like to be able to just access them via that object. It's a great convenience, but there are times when we can run into problems. So let's take an example. So we're just going to start over with an example here. So from 245, we had this homework with schema and models. So our example here is, let's say we have a user model. And in that homework, we had a user who has many book ratings. So they were rating books. And so we said the user model has many ratings. Okay. So this allowed us to join between the user and the ratings table. And so we could find all the books that a user had rated very easily. So let's say we had some code. And we said, users are equal to, take the user model, and we put a where clause on it. And let's say there's some criteria, I'm not going to bother what it is. So we have some criteria that we're going to select on to some subset of the users. All right. So this basically generates a query which is select star from users where blah, whatever that criteria is that we stuck in there. Okay. So that gets us a bunch of users. And let's say we wanted to do something with all these users that we had selected and all the ratings. So we might very well then go users.each, do you, and for each user, let's do something with their ratings, ratings.each, do r. So let's just as an example, just do something simplistic. We'll write out the user's name and the user's rating for all of their ratings. This is just showing that we're going to access something for each user and each rating. Who knows what the purpose really would be, but we're going to have some sort of loop like this. And you could envision that you've got something like this. Actually, you do something like this in a controller, and then in a view, oh yeah, for each of these, I'm going to do this and this, and you end up with these loops. Well, the downside of this is that when we do this portion in here, what this does is it triggers a query, which is basically select star from ratings, where the ratings user ID is equal to our specified user.id. Okay, so we end up with one query here, all right, and we use that data, but then we fire off a query every single time that we have a user. So if we have a lot of users here, let's say we have 100 users or something that we want to show on a web page, we'll fire off 100 queries here. That's boom, 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 boom at the database. That's not very nice. We're basically then, all those reads, because these are reading, we're reading stuff from the database. One, we're using up a network connection to the database, and that's a shared resource, unfortunately. There's only so many connections you can have to the database. We're sending all this network traffic over, and each time that we do this, we're accessing the table for the ratings, and while we want to read from that table, other people can't be changing it. Okay, or it can't be changing certainly the rows for this user and stuff like that. So we end up sort of doing lots of extra work. It's expensive to go out to that database and get stuff back. So this is a bad scenario often. Now, does it bother us when we're working with our small apps while we're developing? Nope. You might notice sometimes that when you load a page and you're watching things in the Rail console, zoom, all these huge number of queries go flying by, and you go, huh, that's interesting, that's cool. I didn't know I wrote so many queries. You know, it's because you got some loop like this. And you're like, it works. Let's move on. And that's absolutely fine. Again, until your website becomes popular. And now everyone is like, why are things slowing down? Why is the latency getting long? What's our problem? All right. It could be because you're not using your database nicely. You're firing off all these queries to it. Now we know that when we have a user model and it has many, we know that we could get all this data, by the way, with one join statement. You know, we could select the username, the rating from users and ratings, when we do the join, and when we could issue one query to that database and get all that data back. And instead, we're doing one query here plus n queries here, so where n is the number of users we get back. So this is called in Rails the n+1 problem. And we don't want the n+1 problem. We would like actually to have one query because we know we could do it in one query. Rails doesn't really make it possible to do it in one query. We can get it done in two queries. You could do it in one query if you wrote the SQL statement to do the join and get back raw data, but unfortunately you're then not working within the nice active record model setup, and we don't have nice models then, and that's probably not what you want to do, but you could do it. You could do one join and get all your data back and display it, but how can we do it in the sort of the proper Rails way? Well, the proper Rails way works as follows. So we've got that, you know, we get our users, but what we change is we tack on and we say includes :ratings. So the table. So we know that we've got this association here, and what we basically do is we tell active record, you know, do this part. So this results in one query. That's the same query as before. And then this, basically, it's like a preload with another query. Okay, so this is the first query, and the second one is to preload. And then so what it does is it preloads the ratings for the users found in query 1. So this query gives us a bunch of users, and then we issue a query here that says select a star from ratings where user ID in, and it gives all the user IDs that we had here. And so we issue one query here, and then it goes ahead and it issues another query to be like, fetch all the ratings for all these users. So we run two queries. It would be nice to, again, only have one join, but at least we do only two queries. All right. And then the big thing is, of course, then when we loop through users and their ratings, there are no further queries issued because that data is all sitting there loaded up into objects for us. All right. Implication, basically, you know, if you have this pattern, where you're going to have a bunch of model objects, and then for each of them, you're going to access data via an association. You should use includes. Okay. Should you start tacking on includes every single time? The answer is no. You shouldn't, because in a lot of circumstances, you're going to do one query to get one user and one query to get that user's ratings. That's just 2 queries. You don't need to go around saying you want this. And if you're just getting the user and you never use their ratings, if you tack on the includes, you're going to always do an extra query that you didn't need. So only in the scenario where you're like, oh, I realize, yeah, I don't want to do these n+1 queries. I just want to do 2 queries. That's the thing to do it. Otherwise, don't go around putting includes on stuff. All right. So those are the big things about using our database nicely. Be sure you have indexes on the columns so that your queries run fast. Don't put an index on every single column. That's a waste of resources. Put them where you need them, okay? 2, again, at the moment, like you do 342 projects, I wouldn't worry about it. Don't go start slapping indexes on things. The scale that we're working at currently is very small. Full table scans aren't going to hurt you, okay? But in future for projects, you should know about, oh yeah, I got a slow query. I probably need to put an index on it. What's the other thing? Well, to reduce latency. All right. Well, so yes, again, we want indices, and we want to watch out for this n+1 problem in Rails. But what else to do to reduce latency? So again, we're back to reduce latency. The first thing we wanted to do was be good database people. Okay, use your database nicely. What's the second thing to reduce latency? The next second thing to do is we should be very wise about cache data where appropriate. And especially from that database. So that we can have caching at lots and lots and lots of different levels. You know, for example, let's say we have images on our website. We can partner and we can use other tools where people will actually cache the images for us that we serve up. And then when a user requests them, rather than us serving them up, they come from a cached location that's actually close to the user, so the user's images, so those images go into the browser faster than if they came from us. There's all sorts of technologies like that. But the most basic one that we need to be aware of is when we're getting data from the database, this is one of the steps that we can do to lower the contention, lower the utilization of the database, is to cache this. So what do I mean about that? So for example, let's say on every web page, we display the user's name. Yeah, we want to be friendly. We want to be nice. We want people to be aware that we know that it's for them. You know, they're logged in currently, something along those lines. Well, at the moment, only thing that we store from page to page, from request to request in our session is an identifier for that user, which then lets us go and look up other information in the database for that user. We don't store their name. So we end up having, for example, to go and hit the database just to go get that user's name. All right. So it's quite possible in scenarios like this where we might really want to actually store the name as well of the user in the session. Okay. There are all these sorts of scenarios where, rather than going against the database constantly, if we know that we'll be able to keep track of when we need to go and look to the database again to see if things have changed. In other words, we should be aware when the user goes and changes their name or something along those lines. We could actually store this data in memory nearby our objects that we want to use and stuff, rather than go back to the database all the time. There are some issues then with the session. Again, we talk about, but doing this, but just the basic idea is, why should I go to the database on every single request if the data is always going to stay the same for the length of the user's session? Why don't I store it in the session object? That's a good idea. Okay, so this is one of the caching data where appropriate is a really big thing. Okay, so those are the two things for reducing latencies. What about the other thing to improve performance? Well, we want to eliminate shared, so we're back to performance. And remember, the first one was minimize latency. And so we looked at ways to do that, which is basically treat your database nice, and then cache data, which also in general for us is going to be caching data from the database. So minimize latency, but then 2 was eliminate shared resources, because this is where we get contention. All right, so how can we go about doing this? What's the value of this? It goes as follows. If we have a situation where this would be great, if we have nothing being shared, then we can scale our app horizontally. To vertically scale an app basically means let's use a bigger machine. Let's use more memory, more processors, or whatever, a faster processor. Let's scale it up vertically. Horizontally actually means by replicating. In most cases, it means by replicating resources. So in our case, we're replicating servers. And so we get a model instead. So user 1, user 2, all the way up to our user n. We'll use something called a load balancer. So the requests actually go into the load balancer, and the load balancer balances them across a set of servers. And so forth. Okay, so rather than just having one machine that has on it multiple CPUs and threads and all sorts of good stuff, we have a whole bunch of separate computers. This is what, this is why you see all those stories about data centers and stuff. And, Google has 1 million computers or whatever they have. Well, part of it is this. They're able to scale horizontally for a lot of stuff. Now, a lot of the apps that we're writing, then everything's still, each one of those connects to our database. Okay. So we still have this database being shared. How do we deal with that? I mean, that's going to be problematic. So in other words, we can run Rails on a bunch of these things. And again, the only place where the data is really has to be shared is there at the database level. So we can actually have a lot of those, but we still have this contention point here with the database. The load balancer is not a contention point. That's just really fast and easy to send the requests on to other servers. It doesn't really do much computation. Well, we talked about caching data. So the big thing really is to cache data like in the user session. So we cache data in the user session. But what happens, so we put something in their session here, and so a user makes a request and it goes to this server and we cache data here. But the next time the load balancer sends them, let's say, to this server, and it's no longer there, and we have to hit the database again. So that's not a perfect solution. And then we would end up with all sorts of data, a whole bunch of session objects across a whole bunch of different servers, and that's wasteful. So one of the things that Rails does out of the gate is that it actually goes and the session object is actually stored back in the user's cookies. Okay, so each time the user makes a request, they send the session and it goes with the request to wherever that request is. And then if you update the session, it gets stored back in the user's cookies, which is handy and dandy. And it's all nicely encrypted, so we don't have to worry about divulging really sensitive data. You shouldn't put really sensitive data in it though, just in case. But, sort of innocuous data, absolutely. But I wouldn't ever want to have, super sensitive data stored sitting here in the user's cookies under the notion that, we assume they won't be able to crack that encryption. So, but what happens, the problem is that the cookie store is only so big. Okay, so storing in a cookies, you can't put much data. What if we want to put if we want to store quite a bit of data and cache it from the database for that user? In that scenario, then often what we do is we make another server where we have basically a fast in-memory store. So this is all in RAM. It doesn't persist to a hard drive. The database persists to hard drives or solid state drives or whatever. That inherently is slower than us just keeping things in RAM and memory. And what we do then is we have connections here. And again, based upon, let's say, a user ID, we first go and we make a read to the database. We get the data we need. We store it to our in-memory sort of fast cache here. And then if the user shows up on other servers, we always have a shared location where we can go and look. It's a shared resource, but it's a much faster shared resource than the database, and it takes load off of the database. Okay. And also, usually, since these sorts of stores are based upon, again, I have a single user ID and I want to look up data related to it, this can actually be scaled out because we can then store different users on different servers. It works quite nicely. All right. So again, caching ends up being often one of our biggest tricks to speeding up performance and by reducing the amount of contention on the database. The database becomes the big sticking point usually in our applications. And so, yeah, we can scale out our servers horizontally. We can do other things, but we still have this single database. Now, there are ways that we can start to try to scale out the relational database. We can make replicas of it, and we can read from those replicas, but we only write to the original database. And so when we write to this database, it writes to the replicas, copies to the replicas that we can read from. there's all sorts of things there. There's all sorts of ways to sort of improve our database design and so forth and so on. We can even, if we realize that we have a set of tables that don't connect with the other tables, sort of because there may be different parts to our application. We can then put those on separate databases. That's great. But eventually, relational databases we're gonna sort of run into performance problems with them as we scale really large. And then we have to look for other sort of storage techniques that allow us to scale out. But when you get to those problems, it's a good sign. You're being very successful. For a huge amount of basic applications that you might write, one database handles it. Okay. And certainly there are some very fancy large-scale database technologies that companies make use of to be able to get things faster. All right. So again, minimize your latency, eliminate your shared resources. Then you can horizontally scale with your servers. You can take the load off of your database by doing things where you keep things in caches and stuff so that you don't have as much contention in the database. But eventually you're probably this is gonna be the sore spot of your performance issues, is the database. All right, that's web app performance, the basics of it.